Welcome to AWS Mastery Labs, turning AWS chaos into clarity with bite-sized tutorials, hands-on labs, and exam-smashing tips. In this video, we'll take a hands-on architectural look at Amazon Elastic Kubernetes Service, or EKS. We'll start by understanding what EKS is, why it matters in modern cloud-native environments, and where it fits in the broader AWS ecosystem. Along the way, we'll highlight key concepts like control plane versus data plane, networking, IAM roles, and integration with other AWS services like CloudWatch, Load Balancer, and ECR. Let's get started. Before we dive into Amazon EKS, it's important to understand the core fundamentals of Kubernetes, the container orchestration engine that powers EKS. At the heart of Kubernetes is its cluster architecture, made up of a control plane and one or more worker nodes. The control plane is responsible for making global decisions about the cluster, like scheduling, maintaining the desired state, and handling API requests, while the worker nodes actually run the containerized applications in units called pods. The pod is the smallest deployable unit in Kubernetes. It can contain one or more containers that share the same network namespace and can communicate over localhost. Pods are ephemeral by nature and are often managed by higher-level abstractions like deployments. Deployments allow you to declare your application's desired state, including the number of replicas you want running. Behind the scenes, deployments use replica sets to ensure that the specified number of pods are always running, even in the face of failures or rolling updates. To make pods accessible to other pods or external clients, Kubernetes uses services. These abstract away the underlying pod IPs and provide stable endpoints. Depending on your needs, you can use cluster IP for internal communication, node port for direct access via nodes, or load balancer for exposing services to the internet. Namespaces are another key feature, offering logical separation within a cluster. This is especially useful for managing multiple environments, like dev, staging, and production, or segmenting access for different teams. Finally, Kubernetes offers horizontal pod auto-scaling, which monitors metrics like CPU or memory usage and automatically scales your pods up or down to match demand, ensuring both efficiency and performance. Amazon Elastic Kubernetes Service, or EKS, is AWS's fully managed Kubernetes offering, designed to simplify the process of running containerized applications at scale in the cloud. At its core, EKS provides a managed Kubernetes control plane. This means AWS handles the heavy lifting of provisioning, patching, and maintaining the core components of Kubernetes, so you can focus on deploying and managing your applications, not the infrastructure behind them. The control plane is also designed for high availability and security. It's automatically distributed across multiple availability zones to ensure resilience against AZ-level failures. When it comes to compute, EKS provides flexible options for running worker nodes. This flexibility lets you optimize cost and performance based on the needs of each workload. One of EKS's major strengths is its deep integration with other AWS services, from networking via VPC and ELB, to container image storage with ECR, to monitoring with CloudWatch and governance with CloudTrail. EKS fits seamlessly into the broader AWS ecosystem. And because EKS runs upstream Kubernetes, you can use all your familiar tools like kubectl, Helm charts, and GitOps pipelines without any vendor lock-in or learning curve. EKS provides scalability and performance at enterprise levels. Whether you need to autoscale nodes based on demand or fine-tune pod-level scaling using custom metrics, EKS provides the hooks and integrations to do so efficiently. AWS also supports EKS add-ons, which are curated and managed components like Core DNS, the VPC CNI plugin, and kubeproxy. These can be installed and updated with just a few clicks or CLI commands, reducing operational overhead and ensuring consistency with AWS best practices. Finally, EKS supports hybrid cloud scenarios and edge computing through AWS Outposts, EKS Anywhere, and Global Accelerator. When choosing between Amazon EKS and self-hosted Kubernetes, it's important to understand the key trade-offs between convenience, control, scalability, and operational overhead. With Amazon EKS, AWS provides a fully managed control plane, which includes the API server, etcd, scheduler, and controller manager. You don't have to provision or maintain any of these components. AWS handles updates, patching, and scaling automatically. In contrast, Self-hosted Kubernetes means you are responsible for setting up and maintaining the entire control plane, including ensuring availability, applying patches, and handling upgrades across versions. EKS is built for high availability out of the box. The control plane spans multiple availability zones, offering resilience against zone-level failures without extra configuration. For self-hosted Kubernetes, you must manually architect for high availability, configuring multi-master setups, external etcd clusters, and failover mechanisms, which increases complexity and operational burden. On the security front, EKS provides deep integration with AWS services. You can use IAM for authentication, KMS for encryption, and native VPC networking, making it easier to secure your workloads using AWS best practices. In a self-hosted setup, you need to configure TLS certificates, RBAC policies, secret storage, and authentication mechanisms yourself, which can be error-prone and time-consuming. When it comes to compute, EKS offers flexibility with managed node groups, self-managed EC2 instances, or even AWS Fargate for serverless containers. This gives you control over infrastructure when needed and simplicity when you want to avoid managing servers. In a self-hosted Kubernetes environment, all compute infrastructure must be provisioned and managed by you, from virtual machines to scaling logic. Finally, EKS includes native support for scaling, offering cluster autoscaling, horizontal pod autoscaling, and managed node groups out of the box. With self-hosted Kubernetes, scaling requires integrating cloud provider APIs or building custom automation workflows. EKS is ideal for teams looking for speed, reliability, and secure integration with the AWS ecosystem, while self-hosted Kubernetes is better suited for teams needing maximum control, customization, or on-premise deployments. Let's take a closer look at the architecture of an Amazon EKS cluster. The architecture is logically divided into two main sections: the EKS account, managed by AWS, and the customer account, which you fully control. In the EKS account, AWS operates the Kubernetes control plane, including components like the cluster endpoint. This endpoint is the primary interface through which kubectl and other Kubernetes tools interact with your cluster. AWS also manages the backend compute, networking, and storage infrastructure that powers the control plane, ensuring high availability, scalability, and automatic patching without any operational burden on you. Connecting the two accounts are the EC2 managed instances, which form the worker nodes of your cluster. While AWS can assist with their provisioning, especially through EKS managed node groups, these instances run inside your customer account, giving you control over configuration, scaling, and security policies. Within the customer account, you integrate your cluster with essential AWS services, the Elastic Load Balancers for traffic distribution, EBS volumes for persistent storage, and VPC networking for secure communication. To enhance cluster functionality, EKS add-ons such as kubeproxy, the VPC CNI plugin, and Core DNS are installed. These add-ons improve networking, enable service discovery, and manage DNS resolution inside the cluster, providing a production-grade Kubernetes environment with minimal friction. Access and authentication are critical components of managing a Kubernetes cluster securely, and Amazon EKS provides a robust framework for both. In EKS, authentication to the Kubernetes API is handled through AWS IAM. Instead of native Kubernetes user objects, EKS uses IAM users and roles to determine who can access the cluster. This is accomplished using the AWS IAM Authenticator, which verifies the identity of the user or service making a request to the Kubernetes API. Once IAM authentication is in place, authorization is governed through the AWS Auth config map, which maps IAM users or roles to Kubernetes RBAC groups, such as system masters, which grants full admin access. For CLI access using tools like kubectl, users must generate a temporary authentication token via the AWS CLI. This is typically done using the AWS EKS update kubeconfig command, which configures the local kubeconfig file with the appropriate cluster endpoint and authentication details. Once authenticated, Kubernetes RBAC takes over to enforce fine-grained permissions. You can define roles and cluster roles that control access to specific API resources and bind them to users or groups. For workloads that need to access AWS services securely, EKS supports IAM roles for service accounts, or URSA. With URSA, you can associate a specific IAM role to a Kubernetes service account, allowing the containers in that pod to assume the role and access AWS services using fine-grained permissions and short-lived credentials. In multi-team or multi-environment scenarios, multi-tenancy can be enforced using a combination of IAM role mappings, Kubernetes namespaces, and RBAC policies. This ensures separation of duties and secure access control between teams sharing the same cluster. Finally, for those who prefer a graphical interface, the AWS Management Console offers a way to view and manage EKS clusters. However, performing actual operations like deploying workloads or modifying configurations still requires the appropriate IAM and RBAC permissions to be in place. In Amazon EKS, choosing the right storage solution depends on the nature of your workloads, whether they need block storage, shared file systems, or object storage. Let's explore the key storage options available. First, we have Amazon EBS, or Elastic Block Store. EBS provides high-performance, persistent block-level storage that can be attached to individual pods via persistent volume claims. It's perfect for stateful applications like databases or message queues. With the EBS CSI driver, you can dynamically provision volumes, take snapshots, and encrypt data at rest seamlessly. Next is Amazon EFS, a fully managed Elastic NFS file system. EFS supports simultaneous access from multiple pods and nodes, making it ideal for workloads that require shared access to files, such as content management systems, machine learning pipelines, or distributed configuration stores. EFS also supports dynamic provisioning using its CSI driver. For object storage, Amazon S3 is a common choice. While not mountable directly like block or file storage, S3 can be accessed from inside pods using AWS SDKs or through tools like S3FS. It's excellent for storing backups, logs, artifacts, and any unstructured data that doesn't require POSIX file semantics. For temporary needs, Kubernetes provides ephemeral storage, like empty dir volumes, which live and die with the pod. This is useful for transient workloads like scratch space or intermediate data processing. For high-performance computing or enterprise-grade features, EKS supports AWS FSx options. FSx for Lustre delivers fast, scalable storage for workloads like genomics and machine learning, while FSx for NetApp ONTAP brings advanced capabilities like multi-protocol access, snapshots, and data replication. Finally, EKS supports data protection through native snapshotting and AWS backup integration. These features allow you to back up EBS and EFS volumes, define backup policies, and restore data in case of accidental deletion or disaster events. Managing the nodes in your EKS cluster is a foundational aspect of maintaining performance, cost efficiency, and reliability. Amazon EKS offers multiple strategies to fit different operational models and workload profiles. Let's start with self-managed nodes. This approach gives you full control over the EC2 instances that make up your worker nodes. You choose the instance types, custom AMIs, and install the necessary software, including the EKS optimized AMI or a custom one. To reduce operational overhead, many teams opt for managed node groups. With this strategy, AWS provisions and manages the EC2 instances for you, including automated health checks, training, and updates. You still have control over things like instance types and scaling configurations. For teams that want to avoid managing servers altogether, AWS Fargate offers a serverless compute engine for containers. With Fargate, you don't need to provision or manage nodes. Just define the pod specs and let AWS handle the rest. It's ideal for bursty event-driven workloads or microservices that need to scale seamlessly. Another important optimization is using BottleRocket, a minimal, hardened Linux-based OS designed for running containers. It reduces surface area, improves boot time, and includes only essential components, making it easier to secure and manage at scale. Cost optimization is often driven by selecting the right capacity type, mixing on-demand instances for stability and spot instances for cost savings. You can configure this mix in managed node groups to get the best of both worlds. Finally, Kubernetes offers powerful scheduling tools to fine-tune workload placement. Use taints and tolerations to dedicate nodes for specific purposes, while node labels and affinities are used to guide the scheduler toward optimal distribution across zones, instance types, or usage classes. One of the key advantages of running workloads on Amazon EKS is the ability to scale dynamically and efficiently balance traffic, ensuring both performance and cost optimization. Let's explore how scaling and load balancing work within the EKS ecosystem. At the application level, the horizontal pod autoscaler monitors metrics like CPU utilization or custom metrics through Prometheus or CloudWatch. When demand spikes, it increases the number of pod replicas. When load drops, it scales them back. This ensures your application scales in real time based on demand without over-provisioning. At the infrastructure level, the cluster autoscaler helps scale the number of worker nodes. It monitors pods that can't be scheduled due to insufficient resources and automatically provisions additional nodes. Conversely, it can also scale down underutilized nodes, helping save on costs. For more advanced scaling, AWS offers Carpenter, an open-source cluster autoscaler designed for speed and flexibility. Carpenter provisions right-sized instances faster than traditional autoscalers and can make better placement decisions across instance types, zones, and capacity types. When it comes to traffic distribution, Kubernetes services of type load balancer integrate with AWS Elastic Load Balancers, allowing incoming traffic to be evenly distributed across healthy pods. For more advanced routing needs, ingress controllers like Nginx or the AWS ALB ingress controller allow for layer 7 routing. This means you can route requests based on path, hostname, or even perform TLS termination, all from a single endpoint. You can also configure internal or external load balancers depending on whether your service is public-facing or restricted to your VPC. This is controlled using simple annotations on your service manifest. Finally, to ensure reliability, Kubernetes uses readiness and liveness probes. These probes help determine whether a pod is ready to receive traffic or if it needs to be restarted, enabling zero downtime deployments and high availability. Security and compliance are top priorities for any production-grade Kubernetes deployment, and Amazon EKS provides a rich set of tools and integrations to help you build a secure, compliant environment without compromising agility. One of the most powerful features in EKS is IAM roles for service accounts, or URSA. This allows you to assign fine-grained AWS IAM permissions directly to Kubernetes pods by linking IAM roles to service accounts. It eliminates the need for hard-coded credentials or granting overly broad permissions at the node level. Within the cluster, Kubernetes RBAC provides role-based access control, allowing you to define exactly what users, service accounts, and applications can do, whether that's viewing logs, modifying resources, or deploying applications. From a network standpoint, EKS can be launched into private subnets, enabling VPC isolation. With private clusters, control plane communication and node access are limited to within your VPC, significantly reducing the attack surface. On the workload level, pod security standards and admission controllers help enforce security best practices, like running containers as non-root, disallowing host networking, and limiting capabilities. For managing secrets, EKS integrates with both Kubernetes secrets and AWS native tools like Secrets Manager and Systems Manager Parameter Store, providing encrypted storage, fine-grained access, and auditability for sensitive information such as API keys and database credentials. To ensure the integrity of your container images, you can leverage Amazon ECR image scanning or third-party tools like Trivia or Claire to detect known vulnerabilities. Some organizations also enforce image signing with Notary to ensure that only verified images are deployed. Finally, Amazon EKS supports compliance with major industry standards and regulations, including SOC 2, PCI DSS, HIPAA, and FedRAMP. This gives your security and compliance teams confidence that EKS is built on a foundation of best practices and validated controls. When adopting Amazon EKS, it's crucial to understand the various pricing components so you can forecast your costs effectively and optimize your spend. First, every EKS cluster incurs a control plane fee. This is a flat charge of 10 cents per hour per cluster. This fee covers the fully managed Kubernetes control plane components, including the API server, etcd database, and core Kubernetes management functions. The next major component is your compute layer, that is, the EC2 instances running your worker nodes. These are billed based on the instance type, size, and pricing model you choose, whether it's on-demand, reserved, or spot instances. If you're using AWS Fardate for serverless pod deployment, billing is based on the requested CPU and memory per pod, charged per second with a 1-minute minimum. Fargate is great for workloads that require elastic scaling or where managing nodes doesn't make sense. Data transfer costs can also impact your bill. While data transferred within the same availability zone is free, cross-AZ traffic incurs standard AWS inter-AZ transfer charges. When you expose services via elastic load balancers, whether it's ALB or NLB, standard AWS pricing applies. You'll pay for each hour the load balancer runs and for the amount of data it processes. For persistent storage, services like Amazon EBS, EFS, or FSX for Lustre are billed based on provisioned capacity, IOPS, and throughput. This is especially important for stateful workloads like databases or machine learning pipelines. You'll also want to account for logging and monitoring. If you enable control plane logs via CloudWatch Logs, or use services like Container Insights or CloudWatch Metrics, those come with separate data ingestion and storage charges. Finally, if you're using third-party tools from the AWS Marketplace, such as for security scanning, observability, or CI/CD, you may incur additional charges from those vendors. Optimizing cost is a critical aspect of running production workloads on Amazon EKS. With flexible compute models and fine-grained control over resources, EKS gives you several powerful levers to manage spend without sacrificing performance. Let's start with the basics, right-sizing EC2 instances. It's common to over-provision compute when you're unsure of your workload patterns, but this leads to significant waste. Regularly assess CPU and memory utilization and match your node types and sizes accordingly to align with actual usage. Next, consider using spot instances for stateless or fault-tolerant workloads. Spot pricing can save you up to 90% compared to on-demand. You can run your batch jobs, development environments, or even parts of your production stack, so long as you're prepared for occasional interruptions. To further enhance scaling efficiency, leverage Carpenter. Unlike the traditional cluster autoscaler, Carpenter dynamically provisions just the right instance type and size based on real-time pod requirements. Speaking of bin packing, another important strategy is to consolidate workloads. Use node selectors, taints, and affinity rules to co-locate compatible workloads. Implement the horizontal pod autoscaler to ensure your applications scale dynamically based on load. This avoids the cost of running unnecessary replicas when demand is low. For unpredictable or bursty workloads, consider AWS Fargate. It's serverless, and you only pay for the exact CPU and memory consumed per pod, making it ideal for spiky usage patterns. Lastly, always use cost allocation tags. By tagging your resources by team, project, or environment, you gain visibility into spend, enabling better governance and potential chargeback models. Use AWS Cost Explorer and budgets to monitor and alert on spend proactively. Monitoring is a critical component of running a resilient and performant Kubernetes environment, and Amazon EKS provides a rich ecosystem of tools to help you gain deep visibility into your clusters. Let's begin with Amazon CloudWatch Container Insights. This service automatically collects and visualizes resource usage metrics across your EKS environment, covering clusters, nodes, pods, and containers. It gives you out-of-the-box dashboards that highlight CPU, memory, disk, and network utilization. Then there's CloudWatch Logs, which captures logs from your application's nodes and optionally the Kubernetes control plane itself. By aggregating these logs centrally, you can search, analyze, and set up alarms based on patterns or anomalies. For advanced telemetry, AWS Distro for OpenTelemetry, or ADOT, is your go-to option. It lets you collect and export traces, metrics, and logs from EKS workloads to services like CloudWatch, X-Ray, and even third-party platforms. ADOT supports standards like OTLP and Prometheus for seamless integration. Speaking of which, Prometheus and Grafana remain staples in the Kubernetes observability stack. Amazon offers fully managed services, Amazon Managed Prometheus and Amazon Managed Grafana. These tools help you track custom metrics, build dashboards, and set fine-grained alerts. For basic cluster telemetry, the Kubernetes Metrics Server provides real-time CPU and memory stats used by the horizontal pod autoscaler and the Kubernetes dashboard. It's lightweight but essential for reactive scaling. To handle log aggregation at scale, many teams deploy FluentBit or FluentD. These tools collect logs from containers and nodes, enrich them with metadata, and forward them to backends like CloudWatch Logs, Elasticsearch, or Amazon S3. Finally, if you're using a commercial observability platform like Datadog, New Relic, or Dynatrace, most offer deep EKS integration, including automatic discovery of Kubernetes objects, log ingestion, metrics dashboards, and distributed tracing. Amazon EKS isn't just a managed Kubernetes control plane, it's part of a rich and rapidly evolving ecosystem. With a wide range of add-ons and integrations, EKS enables platform teams to build, scale, and operate production-grade Kubernetes environments efficiently. Let's start with EKS managed add-ons. These are AWS managed versions of critical Kubernetes components like Core DNS, kubectl, the VPC CNI plugin, and the Amazon EBS CSI driver. AWS handles version compatibility and updates, which significantly reduces operational overhead and risk when patching your clusters. For microservices communication, service meshes like AWS App Mesh or Istio provide advanced traffic management, observability, and security. These meshes integrate natively with EKS and give you control over service discovery, retries, circuit breaking, and mutual TLS encryption. Another key player in the ecosystem is Carpenter, AWS's open-source cluster autoscaler. Carpenter makes scaling smarter by dynamically provisioning the right types of EC2 instances based on pod requirements. Observability is also well covered with Amazon Managed Prometheus and Grafana. These fully managed services allow you to monitor EKS workloads using popular open source tools without managing your own Prometheus servers or Grafana dashboards. To manage ingress traffic, EKS supports multiple ingress controllers. The AWS Load Balancer controller allows you to create application load balancers and network load balancers directly from Kubernetes ingress resources, while options like Nginx and Traefik provide additional flexibility. Finally, for governance and compliance, policy engines like Open Policy Agent or OPA with Gatekeeper or Kyverno allow you to enforce guardrails and validate Kubernetes resource definitions, ensuring that your cluster operates within organizational policies. Thank you for joining us in this video. If you haven't already, we'd love for you to subscribe to our channel to stay updated with our latest content. We look forward to sharing more insights with you in another video. Until then, keep exploring. And thank you for watching.